So hello friends, welcome to Kranthi Physics Tutorials. So in this class we have to discuss about the work energy power. So work energy power is a very important chapter in your first year physics. Okay, so now we have to discuss about the work, what is the work, what is the energy and what is the power. In your intermediate first year and or the class 11, so in class 11, so you have work energy power chapter. So this is very important chapter. So first of all we have to discuss about what is work. So we have to define what is work. Okay, so work, so when we have to set that work is done, so when we have to set that work is done, so whenever some force is acting on a body and the body is displaced, so from one place to another place, so some displacement is occurred in that body. So whenever the force is acting on the body, so then we have to set that some work is done on that body. So some work is done on that body. So here, okay, so here whenever some force is applied on a body, then the body is in moving and the displacement is occurred in that body. So the displacement we consider here S and the force is F, and there is some angle between them for displacement and force, so applied force, so that angle can be considered as theta. So now we have to be said that some work is done on the body. Okay, so now literally, so how we define the work done? So the product of the force applied on the body and the displacement of the body is called as work done. So here the force and displacement is in scalar product. So the scalar product between the, so we have vector product and scalar product, right? So the scalar product between the applied force on the body and the displacement occurred in the body is called as work done here. So whenever some force is acting on your body, then some displacement is occurred in that body, then the product of force and displacement is called as the work, is called as the work. So here work equation can be written as, so work equation can be written as, so W equal to F dot S, W equal to F dot S. So work done, work is denoted by the letter W and force is denoted by the letter F and displacement is denoted by the letter S or D or X, whatever it may be. So here W equal to F dot S. So here force and displacement can be taken in a scalar product. Okay, so now if you can remove the dot product, then what we have to get cos theta term. So W equal to, so F is cos theta. So when we remove, if we remove the dot product, then we get cos theta term. So where theta is the angle between F and S, theta is the angle between F and S. So where theta is the so angle between F and S, theta is the angle between F and S. The force is a vector quantity, S is a vector quantity, but the W, work, is a scalar quantity. So why? Because so in scalar product, so if we multiply the two vectors, so we get the result as a scalar. So that's why here W, work, is a scalar quantity. So that means it has only magnitude, it doesn't represent any direction. What is that? Work. So here this is about work. So here work done is 0. So work done is 0. That means there is no work is done. So when we said that, so in three cases we have to set that there is no work done or work done is 0. So that is when so first one, so force equal to 0. So when force equal to 0, so if we can substitute 0 in place of F, then the total term will be 0. So if there is no force is applied on any body, then the work done is also 0. Why? Because if no force is acting on a body, there is no displacement occurred in the body. So that's why we said that. So when we said that work done is 0, so when force applied on the body, F is equal to 0. And in second case, so displacement equal to 0. In second case, displacement equal to 0. So that means if we can apply the force on a body, but there is no change in the position of the body, that means there is no displacement is occurred in the body. So then also we can say that there is no work is done. Okay. So in third case, so F and S are perpendicular with each other. So that means theta equal to 90 degrees. Theta equal to 90 degrees. So whenever the force applied on the body and the displacement of the body, so both are in perpendicular with each other, that means that one is not possible. So but if force and displacement is perpendicular with each other, so then the angle that means the angle between them is 90 degrees. So if we can substitute the 90 in the cos theta term, so then cos 90 is 0. So that's why the total term will be 0. So that's why, so in three cases, first one is the when force equal to 0, the work done is 0. When displacement is equal to 0, the work done is also 0. And the angle between the force and displacement is 90 degrees, or force and displacement are in perpendicular with each other. So in such three types cases, so the work done will be 0. That means there is no work is done in such type of cases. So here you must and should remember, work done or work is a scalar quantity. So here if the theta, the angle between the force and displacement, if theta is less than 90 degrees, that means the angle is acute angle. So the angle is acute angle. If the theta is less than 90 degrees, that means theta is less than 90 degrees means the angle is called as acute angle. Then the work done can be positive. If theta is greater than 90 degrees, if the theta is greater than 90 degrees, that means the angle is obtuse angle. So the angle between the force and displacement is, if obtuse, that means theta is greater than 90 degrees. So then the work done can be said that negative work done. So that means, so if theta is less than 90 degrees, that means the force between the, that means if the angle between the force and displacement, that means the theta is less than 90 degrees, so that is called acute angle. So then the work done can be said that it is a positive work done. So if the theta is greater than 90 degrees, so that means obtuse angle between the force and displacement, then it can be said that the work done is negative work done. So here the work done is either positive or negative. So we can observe, so when the work is maximum and when the work is minimum. So here the work done Fs cos theta, work done equation is Fs cos theta. So if theta equal to 0, that means theta equal 0 means if theta equal to 0 degrees, whenever we apply the force and the displacement is also occurred in the same applied force, that means the angle between the force and the displacement is 0. So then we can substitute 0 in this one. So cos 0 is 1. So then we have to get so maximum work done. So when we have to get maximum work done, so that angle between the force and the displacement is 0. Now when we said that the work done is minimum. So here we get a maximum work done. We get maximum. So when we said that the work done is minimum. So if theta equal to 90 degrees. So theta equal to 90 degrees means, so the angle between the F and S is 90 degrees. So that means F and S, force and displacement, are perpendicular with each other. So then we can substitute 90 degrees in the cos theta term. So then W is equal to 0. So this is the minimum. So this is the maximum. So here, so when the F and S are in same direction, then we get maximum work done. So whenever the F and S are perpendicular with each other, so then we get minimum work done. That means 0. So work done equation is, so W equal to Fs. Work done equation is W equal to Fs. Now we have to derive the units from this equation. Okay. So F means force. So what are the units for force? Newton, right? So Newton, and S is displacement. So what are the units for displacement distance? Meter. So that's why, so Newton meters. So units of work done are Newton meter. So but this total term Newton meter can be termed as a joule. Okay. So in the honor of the name of the great scientist Joule, in the honor of the name of the great scientist Joule, the Newton meter term can be termed as a, so joules. So that's why the SI units, that's why the SI units of the work done are joule, or joules, or joule. Okay. So now what are the CGS units? So these are the SI units. So now what are the CGS units? So CGS units are ergs. CGS units are ergs. SI units are joules and CGS units are ergs. So one erg is equal to 10 to the power of minus 7 joules. So one erg equal to 10 to the power of minus 7 joules, or one joule equal to 10 to the power of 7 ergs. 1 joule equal to 10 to the power of 7 ergs. So now we have to derive the dimensional formula also from this equation. So you must and should remember, so the units or the dimensional formulas can be derived from the equation only. Now we have to derive the dimensional formula for the work done. So here what is the, so force, here we have force. What is the equation here? So work done is equal to force into displacement. So but work done equal to force into displacement, but force is equal to ma according to Newton's second law. So we can write, so ma here, and this is displacement, this is S is displacement. So here m is mass and a is acceleration. So we have to derive the dimensional formula for the work done. So generally all the dimensional formulas are, most of the dimensional formulas are derived in MLT terms. So here m is the mass, L is the length, and T represents the time. So here what is the equation of the work done? W equal to F into S. But according to Newton's second law, F equal to ma. So here we can write ma, and S is displacement here, right? But here m is mass. So mass dimensional letter is m. So we can write m here. But a is acceleration. So acceleration means, acceleration units are meter per second square. So here meter per second square. Meter means distance. So meter represents the L letter. So that's why we can write here L per second square. Meter per second. Second represents the time here. Letter T. So that's why we can write T square here. So now here this is also displacement. So displacement means it is also distance. So that distance is represented by the letter L, length. So that's why here also we can write L. So that means M L square by T square. That means M L square T minus 2. So M L square T minus 2, T inverse 2 is the dimensional formula for work done. So you can observe how we can derive the units and how we can derive the dimensional formula. So the units and dimensional formula both are derived from the equation or definition, right? So you can observe that.